let's go ahead and get started here. As you recall, at the end of yesterday, we were looking at modal analysis on that 2,000 bus system. And what I'd like you to do is go back into Power World and rerun that system so that you have the data, and then I'll show you how to visualize components of the mode here. Find my cursor. So open up Power World. Load the case ECN 460 TSGC GenDrop. And this is actually a case that we use for undergrad education. So if you think undergrads aren't seeing large systems, they are seeing large systems some places. So we have labs in our undergrad class. We run these in labs, so the students get some feel doing a large-scale system. They don't do modal analysis right now. Okay, so go ahead and run it. Yeah, it's in folder 8. It's ECN 460 _ TSGC. That stands for Texas Synthetic Grid Company. And then it's GenDrop. And just run it. It runs for 15 seconds, and we're just using it to generate the data that we're going to analyze. So after it runs, the next step is we're going to do modal analysis on some signals. And as I said, there's 3 different ways to get into modal analysis. One is to use the icon at the top that's next to the, in the add-ons next to the transient stability. You can load data from plots there, or you can load data from other files like a ComTrade file. We're going to go in just from the transient stability results. So if you view the results from RAM, and we're going to look at substation data here. So if you go to substation, and then I'm going to uncheck all, and I'm just going to look at the frequency average for the substations. And then again, we right click, we go down, modal analysis, all columns, and that brings all the columns into modal analysis, so all the signals. If you scroll down here, you have 1,250 signals. Okay. We're going to do modal analysis on all of them right now. So again, you have to say what start time, what end time do you want. It will default in a simple study like this to the time of the last event. So its start time is 1, end time is 15, maximum hertz is 5, so sampling at 10 times a second. We want to do the iterative matrix pencil, which we talked about last time, so just click that. Iterative matrix pencil, and then it's do modal analysis, and it's done. It did modal analysis on all the signals. So if somebody says to you, here's one signal and I need to know the damping on that signal, it's trivial. Okay? You don't have to count cycles or anything like that. This, we just did 1,500 here, so it is easy to do 1 as well. Okay, so now what I want to do is I want to show you how we can visualize some of the results about a mode. So if you sort up here on damping, the mode that has the least damping is this one that's 0.63 hertz. Okay, as we were developing this, and partially this was done for a project that was funded by BPA, one of the, what were they called, TPA projects? One of the BPA projects. We were trying to figure out how do we visualize this. So we thought, okay, if I right click on there and do show dialog, I've got all the data for each substation saying how that substation's frequency signal contributes into that mode. And it's a magnitude and it's an angle. And we thought, if we can just get this to a substation record, then we can visualize it. So then what we did is we added this up here that says transfer results from selected column to object custom floating point field. This feels a little kludgy and maybe we could automate it, but PowerWorld for all the records has custom floating fields that you can use to display stuff. This data is not yet associated with the substation. This is just modal analysis, which took in a bunch of signals. In PowerWorld, though, because the source of those signals was transient stability, we have maintained a link to the substation record. So we can transfer data there. So we're going to put the angle in the custom float 1, and we're going to put the magnitude unscaled in the custom float 2. To do that, just click on the angle field, angle degree field, and then click on transfer results. And then click on the magnitude unscaled, change this value to 2, and click on transfer results. Now, if you know about pasting and stuff like that, you could have copied this into the clipboard and changed the titles and pasted it back in. Okay, so does everybody understand what we just did?
I didn't get as far as the substation. My computer wasn't going as fast as.
Okay. You're here though, right?
No. I didn't figure out how you selected the substation.
Oh, how we got the data?
I ran the transient analysis, and then I couldn't catch up and figure out where the substation.
Oh, sorry. Let me just go back so everybody's caught up here. If you go, I'll close that. If you go to results from RAM here.
Results from RAM. Results from RAM. Okay.
Yeah, then I stored results for the substation. Go over to the substation tab, which is right there.
Substation. Okay.
Yeah, and then you'll have a whole bunch of fields.
Yeah.
Over here where it says uncheck all, uncheck all of them.
Okay.
And then just check the top one, which is frequency average.
All right.
And then if you right click on any column, you can do the modal analysis all columns.
Okay.
And that brings up this page. Then change the option to iterative matrix pencil.
All right.
Then click the do modal analysis.
All right. So now I'm mostly caught up.
Hopefully you're all the way caught up. Then here, if you find you can sort by damping. We're looking at the one that's got the
628.
Yeah, 628. If you right click on that, oops, I clicked on the wrong one. Right click on that show dialog, then it has this data here, which is showing for each substation how that substation's frequency participated in that mode. And it's a complex number. It's a magnitude and an angle, so it's a vector. Okay, we're going to transfer the angle to the custom float 1 field. So if you click in the angle field and do transfer result, you transfer it to custom float 1. Then 2, if you click in the unscaled magnitude transfer result, it goes into custom float 2. So we've got that right now. Okay, that's over in our substation record. Now we want to visualize it. So we do the geographic data views. We did this last time, so and I gave you the one line. If you just open up now the one line, open one line, it's ECEN sub small. And that opens up that display that we made last time. where it's just got a object for each substation. I'm going to show you now how to change this into visualizing the mode. Okay. If you just select one of these, you get and right click, you get View Geographic Data View Options. Click on that, and it's going to let us customize how the display works. Okay. What we're going to do is we're going to visualize not rectangles, which is what we have right now, but for vectors it's much better to show an arrow. So click on the arrow one right here. That's going to show arrows. And then we really don't want to show the name of the arrow, so on text to show, click none. And then we go to fields and attributes. When you go to fields and attribute, what we want to do now is we want to dynamically size our arrow based upon the magnitude of the modal component. So if we go down to total area, for an arrow, the total area is really just the length of the arrow. Go down there, and then make sure this box is checked, which says it's going to dynamically size that object based on some field. The field we're going to use is the custom float 2, which is where we put the magnitude in. So if you click up to custom float 2, you get that. And these values should then tell you a summary of the data in there that says the minimum value is close to 0, the maximum is 0.25. Everybody got that? Okay. Now this says, how do I relate these, the magnitudes, to a size? We're just going to use a linear mapping, so this should be 0. Set that to like 0.25. So set this to 0.25. And then for a size, I kind of get the size by trial and error. I said 50,000, so use 50,000.
Kind of like a gain on a PI loop.
Yeah, kind of like a gain. That would be a high gain on a PI loop. Okay. And then click OK. And you should see something like that. Do you see something like that? Some people at least got something like this. Okay, and this might look kind of messy. What I'm showing you is something that you only have to do once, then you can save it and use it many times. So this isn't something you do all the time. You create it once. I look at those arrows and I think, that's showing the magnitude, but I also want to show the angle. So what we do is right-click on one of the arrows, View Geographic Data View Options, and we're going to customize it so if I go to Fields and Attributes, the rotation angle, which is right here, that can be dynamically changed as well. So click on Rotation Angle, check this box here, set the field that we use to specify the rotation angle to custom float 1, which is where we put the angle. And then up here it should say the field metrics go from -180 to +180, give or take. So we're having a mapping of -180 to -180, 0 to 0, +180 to +180. So just a linear mapping. Now I get my arrows showing the vector field. the parameters again here are on rotation angle right there. I set this to be minus 180 to minus 180, 0 to 0, 180 to 180. You actually don't need the middle point. Okay, and since I want mine to look pretty good, I'm going to change the thickness of the arrows as well. So you can go up to line thickness. This is an optional one. If you want to make it look nicer, go to line thickness and then check this box to use field lookup. And then you can go up to custom float 2, which has the magnitude. I'm going to set it up so that if it's 0, the thickness is 1. If it's greater than, say, 0.05, I'll make it thickness 2, and if it's greater than, say, 0.15, I'll make it 3. And then I get that. Everyone got that? The thickness is optional. Okay. And we were looking at this, and we thought, yeah, it looks kind of cool, but it also sort of looks like a mess. Because there's like too many arrows, because there's an arrow for each substation. Okay, so then we added functionality to automatically prune this display. So if you right-click on an arrow, you can go over here and do pruning. If you go to pruning, what we do is we ask you how many, it says object pruning to no more than 1 per grid element. We break this into a grid element, and then we get rid of all the objects in a grid. Actually, we don't get rid of them, but we hide them to a 30 by 30 grid, so there's only 1 arrow in each grid element. So if you just do pruning, then you get something that looks more pleasing.
Now, is it just arbitrary which one's selected, or is it average?
Sort of arbitrary.
Mostly arbitrary.
Yeah. There's like other options where
The assumption is if they're close to each other, they're gonna have the same. They might.
yeah, I think you can align retained GDVs with the grid centers if you like it more regular. I mean, there's stuff you can do. But yeah, I mean, the point here is not, I'm just taking one in that grid, not necessarily the one that's closest to the center. Okay, so now you feel good about your handiwork. Save that one line as something. So go File, Save One Line as, and I already saved it as something, I think, like you could call it ECN 460 small sub modes, let's say, and save it. And now you've got it saved. Okay. And if we go back to Modal Analysis, which I closed, you didn't have to close it, but I'm going to go back to the Modal Analysis page, which I can go through from the add-ons Modal Analysis. Let's say I want to visualize another mode. So I click on damping, click on largest percentage, and say I want to look at the 0.32 hertz mode. Everybody got that mode there? If you right click on that, and then do the same thing, transfer the angle into custom float 1, so click on the angle column, transfer results, click on the magnitude unscaled, transfer results, then just click, close, that, you don't even have to close it. Oh, yes, you do, close it. And then when you refresh the display, which you can do by just scrolling, now we're visualizing the 0.32 hertz mode. Okay.
Kind of a weird mode.
Well, right, that mode is West Texas swinging against mostly East Texas. So in WCC, you know, you guys have different modes, you can visualize these modes, and this is just driven by transient stability results. Okay, as long as you've got your buses mapped to substations, and you can create a GDV, you can do this.
And the people use this in post-disturbance analysis?
What?
How people use this feature in post-disturbance analysis?
People are just learning about this feature.
It should motivate you to populate wet cases with substation latitude, longitude.
See,
Because until you have it, you can't use these features. And you need substations. Yeah, you need substations of latitude, longitude.
I've been into this modal analysis stuff for a while, ever since we talked to Jim Gronquist and Bernie Lasser and Alex Borden, and I think Jim said, hey, can't you guys do something with the modes? Tell us the damping. So we've done it, and I've gradually gotten Power World people interested. Jamie's just kind of come on the mode bandwagon in the last few months.
Probably. Yeah.
So he's just understanding this. Like, he asked me, he said, are those numbers, like, are they complex or what are they?
I was looking at them for about a week before I figured out they were complex.
And I said, yes,
You should feel
they're vectors. It's like,
Oh,
you know, it's
yeah.
like, so I've been trying to get this out here. If you're saying, a lot of this could be automated, right? And it's like, yeah, a lot of this could be automated, but it takes people saying, you know, we wanna use this, we find this of value to do it. And it's like, we've written papers on this, and we can do it easily, but people have to say, oh, this is of value, I'd actually like to see that mode. I mean, we can do it, you can color these arrows, you can put contours on them, there's all sorts of stuff you can do it, but if you're not interested, you're not interested. So, we've gotta have somebody interested. Okay. So are there any questions on this? Yes?
If you did this yesterday, since I missed last hour, we can skip it, I'll come back to the video. But when I'm reading those, would you say that like the arrows pointing east, can you interpret that as like the generators are speeding up, the arrows at the same time pointing west might be slowing down and they're kind of going back and forth?
Well, the way to think of it is the mode's going up and down. So this is an exponentially damped mode. And I have made graphs, and you can do this, I'm not gonna go through it right now, but you can make a visualization that just shows this mode. And you'll see it exponentially damp out. So the mode is going up and down and damping. These guys are 180 degrees out of phase with those guys, so they're oscillating against each other. So it's not like one's going faster and one's going slower. At a particular point in time, that's true, but then they switch around.
So that other one that you did that was least damp, that had more of like a tornado look, it seemed like they were all in more, not like 180 degrees apart, but they were all going more together, just shifted a little bit.
Well, yeah, I mean, they were like going around in a circle.
Is that sort of power flow is sort of,
But I was guessing that the Mexico system doesn't exist, so I was looking at the Texas boundary, sort of like your ends of the system. But I would assume you would need things going up and down at 180 degree separation like this one shows. So how's that other mode? Maybe I have to look at it again.
It's more like the wave than.
It's like,
Oh, okay.
You know what I mean?
the answer
Oh,
is,
okay, that makes sense.
You know, it's just oscillating around the system. That happens in WEC. Isn't there a mode that kind of goes around the band?
well, the thing is that you guys can visualize your modes now.
Yeah.
And when I saw that, I mean, we got a response that was going around in a circle, and I'm like, what is this going in a circle? And I said to my students, I said, why does that mode exist? And of course, they didn't answer. but I asked a question sort of saying, tell me why that mode exists. Or why does this mode exist? In what physically is creating that mode, what is creating that mode? But you know, now you can visualize it and it's like, yeah, that's really there in the results. You see that. Okay, so it's, and in WECC you guys have modes. The East doesn't understand their modes as well as the West, but we can take an Eastern interconnect case, run it, and show all their modes. I mean, it's more data, because if we ran all the substations in the East, it'd be like 60,000 substations or something, or 50,000. But we can do that, you know, and start visualizing them. We're going to do a project for SPP where we're combining the West and the East, and we're going to run it all together and see what happens. So if I say I take these AC lines and join the West and the East, what is the worst situation? You know, and that's what we're going to investigate. Could they be combined or not? I mean, what would be the worst situation for combining them?
Slow power flows.
What?
Slow power flows.
Well, yeah, that's true. Yeah, well, that's why Texas is good. I don't think Texas is separate just because we like to solve smaller power flows, but it is a nice, you know, it is a nice consequence. Okay, I will finish up here pretty quickly by showing you how we can visualize the source of an oscillation. Okay, so we did that one. This is one where I put some color in there just for fun. Okay, did that one. Yeah, on this one, I don't know why it circles, but it does circle. And you know, there's kind of, it's a different mode. Okay, visualizing the source of oscillations. We can do this mostly automatically in Power World. I'm going to show you an example right now. This is going to show a forced oscillation in our Texas 2000 bus system, where I just took one generator and started it oscillating, okay? And it's oscillating at 1 hertz, and the visualization is a contour of the frequency going from 59.95 hertz to 60.05 hertz. Okay, when I show you this, tell me where the source is. That's running in real time. So if you're seeing that, where's the source of that oscillation? I'll do it again.
Houston.
Houston?
Dallas.
Yeah.
I don't know what's the
Houston?
Austin? Yeah, Houston's on the coast.
Yeah.
You guys don't know where it's
I don't know where
Where
the
the
second
red
part
is.
This is Houston down here.
That's
That's
good.
Yeah.
Okay, so San Antonio.
This is Houston, Austin, San Antonio, Dallas, Fort Worth.
Houston,
Yeah, so it looked like Houston was leading, and that's where it is. But let's now pull that out of the data. So if you load up the case, close the modal analysis form for right now. Load up the case ECN 460 TSGC underscore 1 hertz oscillation. This is where I put one of those signal generators at a bus, and we now know it's somewhere in the Houston area. Go ahead to add-ons transient stability. And run it. Now in transient stability, there is no event. I've got my signal generator set to start at like 1 second, and it just starts oscillating at 1 hertz, and it drives the whole system with it. So if you run transient stability, and it's going to run for 15 seconds, you're going to get some results there. Okay, so let's say you're presented with a case that has like a persistent oscillation in it, and you want to figure out what's going on. If you look at, you know, we can visualize in Power World easily all the frequencies. That's what all the frequencies look like. And of course here, you could kind of see where it starts. But let's say you didn't know that. Let's say you just had real-time data coming in from PMUs and you wanted to figure stuff out. So we'll go to modal analysis. So close all of these, results from RAM. We're going to do the buses now. If you go to buses and then uncheck all, and we're just going to look at the bus frequency, this shows the frequency of all 2,000 buses in the case. Okay, everybody got that? Okay, right click on there and do modal analysis all columns, and it brings this up. Check the iterative matrix pencil method and then click do modal analysis, and it quickly does all 2,000. And surprise, surprise, we get a mode that is right at 1 hertz with essentially no damping. And it's like, that's because that's my forced source. I was forcing it. If you gave me a set of signals that had some forced source, and it might be a very small source, because this was a big source, so it was easy to see, but it could be a small source. If you gave that to me, and I use this tool, I'm going to see it. It's going to pop up here as something with essentially zero damping. So now if you go and you right-click on that and look at that, you can look at the values that we just showed, and we could visualize this mode if we wanted. Okay, I actually haven't done that. I'm sorry, we don't want to do bus frequency, we want to do bus angles. Close that, go back, close the modal analysis, go back and change it from showing frequency to bus angles, which is V angle, and uncheck the frequency one. So I'm sorry, oh, it's like my computer one. Yeah, so close the modal analysis form, go back to the transient stability results, results from RAM, look at bus, and then uncheck all and check V angle. I think I've got it, that's it. I don't think I saved it. The good thing is a small case, so go to results storage, and under the bus option, tell it to save. So go to results storage, buses, and then we were saving voltage magnitude, save the voltage angle as well. So if you right click on there, you can do under set toggle all yes, and then rerun it, saving the bus angles. I thought I had that set. So now results from RAM bus, and we should have V angle, so we should have the volt angle there. Everybody there? Okay, when you do modal analysis, it just takes signals. So it could be frequency, it could be angle. Again, do the right click, modal analysis, all columns, iterative matrix pencil, and for the start time, we started at oscillating at time t equals 1. Maybe if you set the start time to 5, it would be better, because that's where it's really kind of all going together. So just set it to 5. And then do modal analysis. And again, it runs fast, and it picks up that 1 hertz with essentially no damping. Now right click on that and do show dialog. Everybody got that? Okay. If you do that, there's a secret button. The secret button is visualize source of oscillations. Usually when an oscillation occurs, you get data, and a lot of times it's hard to tell the source of the oscillation. In transient stability, we can take advantage of the fact that we've got potentially all the data, so we can look at phase angle differences between buses, and we can actually pretty effectively visualize the source of oscillation. Because if there's a forced oscillation, something is leading that oscillation. Something's pulling the system ahead, so that would have a leading phase angle. So if you click on that, visualize source of oscillations, it looks like it doesn't do anything. Okay. What it does is it calculates the mode power flow on each line and places a value in the line's custom float 1 field, calculates the net mode power injection at each substation, stores it in the substation custom float 1 field. Okay.
Everybody get that?
It's not a test at the end, but it's at least written down, okay? And then what you can do is, if you have a substation GDV, which we just created, and you visualize this field, the source of the oscillation pops up. So if we go to here, I guess I need to close that. I open up that substation GDV. So I'm going to open a 1 line. The sub small should work. If I open that one up, I guess I already got it open. If I visualize the custom float 1 for the substation, total area, and I make it proportional to custom float 1, it gives me metrics, a minus number and a plus number here. So I'm going to go from minus 400 to plus 400, and I'll tell you what that means in just a second. And I'm going to scale it. Let me put a 0 in there. So if I want to put a 0 in, I just right click and do insert, and it'll insert a 0. And the one that is largest is the source of the oscillation. And there's a bit of math behind this, but to kind of show you a little bit more here, what we do is, because we have the modal component of the forced oscillation, the 1 hertz oscillation, we have the magnitude and angle of how the angle at each bus is changing, we can estimate a modal line flow, and then we calculate those values and we just say which substation is producing the most modal power, and then where is it being absorbed. The one that's producing the most is the source of the oscillation. Okay, now, and then I can visualize it with the GDV. This is research stuff that we're doing, and we're trying to see if people are interested in this to add into study tools. Okay, if you're interested in the source of forced oscillations, in study tools there's ways to do it. We just need somebody to get interest, because I developed this, and we actually developed this for a research project. I can put it into Power World, but then I have to get somebody like Jamie interested enough in it to like take it to the next step. And Jamie says, well, we need customers interested in it to take it to the next step. So we can do lots of cool stuff, and you're seeing. What?
I said you just heard our quarterly conversation on the phone.
What?
I just say you just told them what we talked about every 3 months.
Yeah.
That's cool, Tom. Yeah.
Yeah, so, you know, like the iterative matrix pencil method, the fact that it tends to work pretty well is a nice thing. So we're trying to get it out and get it used and make it as easy as possible for people to use this. And this visualization of the source of oscillation is another step beyond that. But, you know, we're going one step at a time, but we can do a lot with this. And just getting people interested in the GDVs is something that we're showing use for them. It's, you know, you just need to know if people are interested in them.
How well does this work when you have multiple bad culprits?
Bad what?
Culprits, like a lot of, you know, a couple units that are causing oscillations instead of just, you know, one main source.
Simultaneously at the same frequency?
Well, they wouldn't be at the same frequency.
Or maybe it's like a control system driven on like one PDCI is fighting some other device, and so they're just going back and forth with each other based on their controls.
Well, right, and I did say it's research only, so we'd want to look at that. There was a paper on this from someone from PNNL, and I just gave a presentation on this to the WCC Oscillations group. And one of the issues is how well does this work if the force frequency is close to a natural mode? And it works still pretty good. If I had to say, what if there's two forced oscillations that are separate on the system, in the interest of trying to do this in real time, we've got this case that has a 1 Hertz oscillation on it. Let me cause another generator, unpleasant, show dialog. I'm going to delete its exciter or just deactivate it, and then put in an infinite bus generator, and we'll start it at time t equals 1. We'll make the deviation the same as before, 0.05. And what frequency do you want?
200 hertz. No.
Okay, let's not do 200 hertz. Okay, we got a 1 Hertz mode. So what if I put in 0.8?
What about another 100 mode but out of phase? Like 180 degrees, like it was fighting the other unit.
I don't know that I can control the phase angle here. And I'm thinking not. That would be something we could add in if people say, hey, we want these with different phase angles. But I don't think we've got that right now. I'll put it at 0.8 Hertz. I mean, this is something, you guys have the case and you can play around with it. it's a small enough case that you can run it. You know, there I'm running it now. I've got the two of them in there, and Lord knows what they're doing, but you know, it's like that's kind of like the results that we're getting with two of them. What's going on there, I don't exactly know. Okay. I've got some voltage collapse going on in the system. If I were to, that's kind of interesting. And I'll finish with this. If I saw this behavior and I wanted to understand it, I might make up a contour movie really fast. And they actually provide a lot of insight into what's going on in the system. So this is just going to be a contour movie that we're generating on the fly here. Substation, TS average frequency. I got to set my contour options. That helps.
It's like a waterfall.
Yeah, and I don't know what's going on with the other one, whether I disabled that or what, but, no, yeah, there goes the other one, so, you know, I don't know what's going on here, but making up this movie would help in understanding it. We had this situation, so I won't let this run through, but this is them interacting, then you could go on and see whether it works or not. We were working on a project for BPA, and we were studying a system, and this is a frequency visualization, and I was looking at the transient stability results, and I thought, this is like really weird, what is going on? And then I visualized it, and it turns out that the system's oscillating. But I looked at that for a long time, looking at the data, not the visualization, and did not know what was going on. And once we visualized it, then we could figure out what the problem was, and it was an equivalent model. It just turned out there was bad data on a generator there. But sometimes making these visualizations, which you can now do really fast. I mean, I just showed you kind of in real time how to do it on this Texas 2000 case. You can get a lot of insight into your case very quickly. So it's something that's useful to do. Okay, so I'll leave it at that. Are there any final questions on this?
What parameter was that last one?
Bus frequency.
Oh, I was visualizing bus frequency.
Okay.
Yeah, it was a 2,000 bus equivalent case that we were making up to do some testing for a BPA project on, and we got this really weird result. And we tracked it down to a bad model in a generator in Wyoming. And when I fixed it, which I showed at the end, I fixed the parameter. Actually, I just turned off the generator. Yeah, that's the usual fix. But the takeaway is, this was prior to all this modal analysis. If we had the modal analysis, I would have done that, and I would have got a lot of insight. We didn't have that then, so we just had the visualization. So there's a lot of tools here. You know, obviously you're not going to use these in a lot of situations, but if you're trying to understand a case, you can use them. What Jamie's going to talk about right now is how we can automate this tool. And yeah, we're starting to. So the idea is you say, okay, I'm doing 1,000 runs. I don't have time to do modal analysis on each one. can you automate it? And the answer is maybe.
Maybe, eventually.